Welcome to ePG Pathshala lecture series on computer science. In this module on data analytics, we will be continuing discussing about mining data streams. As part of this module, we will learn the basics behind sliding window concepts in data streams, understand the basics of how to count bits and numbers in the given data stream, and the approach called DJIM approach used for counting the number of ones in a given data stream. First, we should understand how querying on sliding window may be done. These queries are executed over the given data stream and a specific set of elements is highlighted by a window. So, when you want to run a query on those specific set of elements, then how are we going to do it? This is what we are going to discuss. As part of this discussion, we will be understanding inside that window, we will be counting the number of ones using a method called DJIM method. Let us start understanding how queries can be executed over a sliding window. Here in this scenario, we are going to consider a sliding window whose length is very large. So, ultimately we are working on a lengthy sliding window. Now, this model may be very useful for running queries on a fixed window size whose length is n, where n indicates the most recent elements that has been received. Now, let us take a scenario. Consider Amazon, which is selling multiple products over the web. Now, if it wants to understand which of its products in the current scenario is widely purchased, or for which of its products there is a larger demand, then you should work on say a specific time window, and in that time window you should verify for the various transactions that has happened, and among the transactions you will have to look in for the presence or absence of a product which is indicated by Amazon. In this scenario, you are going to work on a sliding window which identifies or highlights say the current scenario or the scenario which is essential for our analysis at present point of time. Over that sliding window, you will be running algorithms that may identify the number of elements or the number of ones or even say the number of products in real world for better understanding about the demands of various products. Say the interesting case here is in stream processing environment. When we discussed about the stream processing model, I have already mentioned we have limitations on our main memory. Therefore, we may not be in a position to hold all the n elements that is present in the given data stream, because we have a limitation. In such scenarios, you cannot work on the entire stream. Instead, you can have some aggregated information over the previous stream, that is the past stream elements, and whatever element the sliding window currently highlights, you can work on the current elements and combine the aggregated information over the past and the current elements that are available in the sliding window. So, this is how it can be executed. Now, let us come back to the Amazon scenario. Now, assume for every product X, you are going to have either a 0 or 1 in the data stream, indicating whether the product was part of a transaction or not. Now, how many transactions you are going to have is you are going to hold n transactions within a specific time window. Now, if we want to answer queries, how many number of times Amazon has sold say the product X in the last or the recent K sales means, then you will have to define a window whose size is of K, and in that K you will have to identify how many transactions contain the product X. This is fundamentally very difficult. The reason is the window that you are going to highlight indicates only the most recent elements and the older information may not be available. Secondly, the sliding window may hold only part of the recent information. So, when you want to come up with an analysis of an entire data, this becomes a bit difficult. So, with all these challenges in mind, let us understand how this sliding window works. Now, sliding window, if you want to analyze, assume the window size is 6, that is it can hold n elements. For example, if there are going to be some transactions, then the sliding window currently will hold 6 transactions. Now, in those transactions you can either make use of a value like 1 or 0 or even integer information for the purpose of understanding the presence or absence of an entity or say a product as mentioned in the Amazon scenario. If there is going to be a set of streams as shown here, now the window of size 6 highlights say 6 elements available in the data stream. Now, in this stream you can find the older information are available on the left hand side and the recent or the newer information will be available on the right hand side. So, what does indicate is as you move from left to right along the stream, you are working with respect to the current time scenario. Now, as the time passes, what happens is the stream will also move, that is new elements will arise. Therefore, what may happen to the sliding window is we will get a feel as though the window is moving one time ahead. In other words, the window is going to highlight the most recent 6 elements. Take the another example where say one more new element has been added. In this scenario you will find now the same window whose size is 6 is going to highlight the next recent 6 elements and so on. But when you take a look at this picture, you will get a feel as though the stream is fixed, that is static, but the window moves over the stream, and that is the reason why it is called a sliding window. So, to summarize, when we talk about sliding window will highlight elements which have occurred earlier on its left and the elements which is currently there inside the window and the elements that may occur in the future towards its left. And since the window highlights the most recent element based on the size fixed by say the individual or the analyst, we will have a look as though or we will have a feel as though the window is sliding over the given data stream. Now, what is the problem of counting bits? Suppose your stream is made up of zeros and ones like the one shown here, and let us assume n, the window size is equal to 6. Now, we will have to answer queries like how many number of ones are there in the last k bits, where k is very less or less than equal to n, where n is the size of the window. Now, how this question may be answered is you will have to first take a look at the most recent n bits. Having identified the most recent n bits which is highlighted inside the window, then you will have to work on say the new bit that is coming into picture. The problem here is should I include the n plus 1th bit? Now, how this may be decided? This may be decided based on the chance or a specific weightage. If a new element that arrives at say the n plus 1th time satisfies the weightage or satisfies the constraint, then the element may be considered, else it may be ignored. But when we are trying to get an exact answer, this may not work out. The reason is the window is going to have a smaller length, and therefore, we are not covering the entire element from the beginning till the end. So, the answer that we are going to get is going to be an approximated answer, it is not an exact answer. Now, what exactly is the problem over here? Suppose if we cannot store all the n bits that occurs at a specific point of time. For example, if you are going to have say 1 billion emails, then your window size should have 1 billion bits. Every bit will indicate either the presence or absence of a specific email or say presence or absence of an email from a specific person. Now, what may happen is we may not expect what will arrive in the future. With this uncertainty only, we are going to work on the current window. Therefore, the answer that you are going to get is going to be a prediction which in many scenarios will be an approximate answer. But what is that is very good over here is, though the answer is approximate, to 90% extent that approximation is always correct. So, it is always good to work with certain approximations that may be results of prediction scenarios. One simple solution for the given problem is, if I am going to count the number of ones that are in the last n bit, we need to first assume the elements in the data stream are distributed uniformly. If this uniformity assumption is made, only then we can make a proper prediction. For this, what is that you need to do is, you will have to maintain two counters. One counter for highlighting the number of ones from the beginning of the stream, and another counter for indicating the number of zeros from the beginning of the stream. Now, if your analysis is all about ones, then you will have to work on, say, the number s. If your analysis is about the occurrence of zeros, then you will have to work on the variable z. In our scenario, we are working on the number of ones, how many ones are in the last n bits. Now, this will be given by the probability n multiplied by s divided by s plus z, where n is the length of the window. In other words, the number of elements that can be accommodated in the given window, multiplied by s is the number of ones occurring from the beginning of the stream, and z is the number of zeros occurring from the beginning of the stream. So, n multiplied by s divided by s plus z will provide you the probability, and that indicates what is the percentage of ones that may be available in the given data stream. Now, I already mentioned you will have to make a uniformity assumption. If suppose if the stream is not uniform, in other words, if the distribution is going to change over time, then this approach may not work. Therefore, you will have to go for an approach called DGIM method. DGIM indicates Datar, Gionis, Indic and Motwani. The four are the authors of this particular method. So, these four authors have proposed a method which assume that the data elements are non-uniform in terms of its distribution. In other words, they assume that the data elements does not assume uniformity. In other words, non-uniformity is exhibited. Now, for working and a solution for this particular method, we assume that the data streams are stored in the order of log n square bits per stream. In this complexity, by usage of log, we can understand the order of search or the order of storage or the order of access reduces drastically. But one important factor which we need to analyze here is what will be the percentage of error, because already I told you such methods will only provide an approximation of the counts. So, therefore, we will have to look at what percentage of error may come into picture, and this methodology proves that it reduces the error by greater than 50%. So, they actually compute the error factor which can be reduced by a fraction f which is greater than 0 in many scenarios when you work on how are you going to save the bits per stream. So, the total size of the memory which you are going to make use of decides the complexity of the algorithm. Now, the idea of DGIM method is, it is based on exponential windows. As the name indicates, exponential windows means the size of the window varies exponentially. But this particular methodology, though provides an approximate answer, it may not work in all scenarios. The reason is they assume the data elements are non-uniform in terms of distribution. So, what is that they are trying to do here is, they are trying to summarize exponentially increasing regions of the stream looking backward here in the sense looking over the past. So, when you take a stream like this, on the right hand side we assume we are highlighting the most recent element, and on the left hand side we assume we are encountering the oldest element. Now, the size of the window, when you take a look at it, it is going to be decreasing from left to right. In other words, for the past the window size will be high, and as we move towards the present, the window size will reduce drastically. That is the meaning of summarize exponentially increasing regions of the stream looking backward. Backward here is the past. Now, what is that they do is, they drop small regions if they begin at the same point. For example, here you find say a window which comprises of 3 elements beginning at this point. Similarly, another window which comprises of 4 number of ones inside this window also starts here, and there is one more window that comprises of 10 ones inside this window beginning at the same point of time. So, you can always drop the smaller regions 3 and 4, and instead you can work on this larger region because all these smaller regions begin at the same point. So, what happens is it provides you a view as though the windows are merged as you move towards the past or as you move towards the older data. So, what is that we can construct here is we can reconstruct the count of last n bits because it is going to be available in the window, and we can make sure that the last ones, that is which are going to occur in the maximum sized window, is also included in the n value, that is the total window size. So, what they are trying to do here is they are trying to define the sliding window length based on the total number of bits or the number of ones which is essential for our analysis. The advantage of this particular methodology is, as I already mentioned, it stores only log n square bits. How this happens is log n counts of log n to the base 2 bits are considered and they are stored. Therefore, the product of this is log n square. Now, when you are trying to work with respect to bits, that is when new bits comes into picture, it is very easy to update more and more bits as they enter. All that you need to do is you need to look in for a specific criterion. So, you either accept or ignore it, and the error is going to be not greater than a number or a value which is indicating the number of ones in the window of length n. That is, we are going to have an unknown area. The unknown area may be the number of elements that arrive at the or in the past. We are trying to work with respect to an error in the past. When you are trying to work with respect to an error in the past, you need to identify what elements may arrive in the near future. So, the unknown area over here indicates the future elements that may arrive to your model, and in this unknown area DJM method provides an error count which is very less when compared to the number of ones identified by this particular method. These are the advantages. Now, what may be a drawback with respect to this particular method? Now, as long as the number of ones are fairly evenly distributed, the error can always be less than 50% or in other words no more than 50%. But when the number of 1 and its distribution in the unknown area, that is at the end, is not known. Now, what I told was when we are trying to work with respect to the unknown area, it is the past. Now, with respect to the past, you will have to work on the present elements. So, if the distribution of ones in this unknown area is not known, then the percentage of error may sometimes be more than 50%. This error becomes highly complex and it becomes unbounded. This is actually a drawback of DJM method. Now, what simple change may be done to a DJM method is, that is in order to overcome this error is, instead of summarizing a fixed length block, we can summarize blocks with specific number of ones. That is, the block sizes over here indicates say the number of ones available in this box. Already we have discussed that the window size is going to be exponential. In this scenario, if you are going to modify the window size as the number of ones, then the number of ones inside the window is going to increase exponentially as you move from right to the left in a given data stream. For example, if this is a bucketized stream, you will find say there are two size of buckets 1, that is this bucket can hold only one value. Then you have one bucket of size 2 indicating there are 2 ones in the bucket. Then you have two size of buckets 4 indicating 4 ones inside this bucket. So, take this bucket 1, 2, 3, 4. Similarly, in this bucket 1, 2, 3, 4 ones are there. Then you can come up with 2 buckets of size 8. The 8 over here indicates the number of ones in these buckets, and at last, that is in the oldest data you will find say a window, but this window is going to be partial. The reason, we may not know what is in the past, that is after this window. So, we will have at least one window whose size is 16 indicating 16 number of ones in the last bucket. So, when you take a look at the size, it is nothing but the number of ones. When you take a look at the ones, it is actually an exponential information. So, the size of bucket here is 1, which is indicated as 2 to the power of 0. The size of bucket is 2, indicating a bucket whose size is 2 to the power of 1, and here the bucket size is 4, which is indicated by 2 to the power of 2, and here the bucket size is 8, which is indicated by 2 to the power of 3, and so on. So, you find the window size is increasing exponentially, where the window size indicates the number of ones. When we talk with respect to DGIM method actually has various timestamps starting from 1 to till n, and the most recent element will be always on the right hand side. Now, it is these timestamps that are very essential for understanding or for counting the number of ones. Normally, timestamps will be recorded as modulo n, where n is the window size, and hence the relevant timestamps can be recorded in the order of log n to the base 2 bits. Now, when you talk about the DGIM bucket, I already told you the timestamp is represented as, say, an order of log n to the base 2 bits. So, the timestamp which is towards the end here in the sense in the past, is going to have a size of order of log n bits, and the number of ones between its beginning and ending is going to be represented as log of log n bits. What is the constraint is? The constraint is the number of ones must be to the power of 2, which indicates clearly what must be the number of ones between the beginning and ending of a given stream. So, which is going to be order of log n. Now, when you represent streams by bucket, what things you can do or what constraints you may apply? You can always retain either 1 or 2 buckets with the same power of 2. In other words, there can be maximum of 2 buckets of the same size, and the size must be to the power of 2, where the size indicates the number of ones, and buckets do not overlap in timestamps. So, every bucket that we are considering will be associated to different timestamps. Buckets are sorted by size, that is, as you move from left to right, the size of the bucket decreases. In other words, the earlier buckets will have a larger size when compared with the most recent bucket, whose size will be smaller, and buckets disappear when their end time is greater than n. In other words, we ignore few data elements or streams after a timestamp n, which is indicated by means of the length of the window. Once again, take a look at this bucketized stream. Here in this bucketized stream, we find buckets whose size indicates the number of ones, and this size is always represented to the power of 2. Now, there are certain properties which need to be satisfied by the bucket, which is maintained under DGIM approach. What are those properties? As I already mentioned, you can always have maximum of 2 buckets of the same size. Now, when you take a look at this data stream example, you may find, say, a bucket of size 1 occurring maximum of 2, and another bucket whose size of 2 is occurring exactly 1. So, either you can have a bucket of the same size exactly 1 time or at the maximum of 2 time. That is the first constraint, and implicitly these bucket size must be power of 2. Secondly, the buckets that are indicated here are not overlapping. They are all associated with clear cut timestamps. Therefore, the buckets do not overlap in terms of the timestamp. In case if it is overlapping, then the scenario becomes a bit complex, and you have to introduce one more time variable to indicate the intersection of the timestamps. And the third constraint is, when you move from the left to right, the bucket size decreases. In other words, the buckets are sorted by their size. So, if it is from left to right, means it is in descending order. If it is from right to left, that is from the most recent data to the oldest data, means the bucket size will be small to larger. In other words, it is going to be ascending in order. That is, here it is going to be smallest size, and towards the left you will be having the largest sized window. If these 3 properties are satisfied, only then it can be called as a DGIM approach. And as a result of this approach, instead of holding a window of fixed size, here you are trying to work with respect to a window whose size indicates the number of ones. So, actually speaking, you are reducing the complexity of this algorithm. Now, suppose if you want to update these buckets, that is when a new element n, that is assume this is the most recent element. Suppose when one more element comes into picture, assume the time here is n. So, when the new element comes, the element may be indicated as n plus 1. So, while you are updating a bucket, when a new element comes, that is the n plus 1th element comes into picture, then how are you going to consider the new element? What will happen to the older element? Now, as per DGIM method, the older elements will be dropped. In other words, the elements on the left hand side will be dropped for the purpose of accommodating the most recent element. There are actually two cases, that is either you may have a 0 or a 1 element coming into picture. If it is going to be 0 means, of course, there is no issue, you are simply going to ignore it. So, no change at all is essential. Suppose if you are going to encounter the current bit which is highlighted by a value 1, then what is that you need to do is, you need to first create a new bucket of size 1 for holding this single bit alone, and then you will have to have the timestamp assigned to the current time. Now, if there are, assume you have a bucket whose size is 1, earlier had you identified 2 more such buckets, that is currently you are having 3 buckets of the same size. So, earlier you had 2 buckets of size 1 and now you have one more, that is the third bucket of the same size. In such scenarios, what is that you need to do is, you will have to combine the oldest 2 elements and then you will have to retain the current bucket alone. So, when you merge the oldest elements or the oldest buckets, then you will have to see to that the number of ones in the bucket must be to the power of 2. Suppose if there are now 3 buckets of size 2, then you will have to combine the oldest 2 buckets of size 2 and this has to continue. So, what may be affected is, from the right to the left, merging of buckets will come into picture, and when you are merging towards the left, the oldest elements will be ignored. This is what will happen when you make use of DGIM method. Now, this diagram, this example indicates how buckets are updated. Assume the first scene is, you are looking at the current state of the stream. Here in the current state, say this box indicates this one, the second box indicate the second one, and the third box, yellow color box, indicates say the 2 ones. Now, what is happening is, when a bit value, new bit value 1 arrives, you will have to create a separate bucket for this value 1. And now a scenario comes into picture. The scenario is, already you have 2 buckets of size 1 and now you have one more bucket of the same size. Therefore, 3 buckets of the same size is arising. Now, you will have to merge in such scenarios. If such condition arises, you will have to merge the oldest 2 buckets. So, when you merge the oldest 2 buckets, you will be finding the 2 ones coming into the same bucket. So, now you have the most recent bucket indicating the most recent element and the older buckets merged together. Now, when the buckets are merged, you will have to verify what happens to the previous. In case if you find in the older data already 2 buckets of the same size are occurring, and because of this merging one more third bucket comes into picture, then you will have to merge the oldest 2 buckets, and this iteration will go on until you encounter many new elements. Now, how to query? When you want to query, you will have to sum the size of all the buckets and then you will have to add half the size of the last bucket. Now, when we are doing so, we should know that the number of how many number of ones are there in the last bucket and what is the quantum of the one which need to be added. The error when you are computing, it will be 50%. How this error is going to be 50% is, if the bucket last bucket size is 2 to the power of r, assume we are going to take half of it, then it is 2 to the power of r minus 1. So, the last bucket size 2r and it is going to contain at least 2 to the power of r minus 1, which is equal to 50%. Few applications of DGIM, say instead of the number of ones, it can even indicate say a value highlighting the count. Sometimes it can even be say an integer. In certain scenarios, you can make use of say positive values highlighting say the average price of a particular element that may be associated to various transactions happened over a period of time. Then you can easily calculate the number of times the particular item has occurred and the average of the particular sale. So, to summarize, counting the number of ones in the recent or the last n elements is done using an exponentially increasing window. This approach can be extended to the last k elements by means of having either ones or an integer value, and accordingly various applications of counting ones will come into picture. Thank you.